In analysis, you meet many different types of function. Some functions are very well behaved, like these ones, functions which arise naturally in many problems. Well, this function x squared is continuous everywhere, that is, on the whole of R. So it has no jumps. It can be drawn without lifting your pencil from the paper. And that's also true of e to the x and of sine x. And if we exclude 0, 1 over x is also continuous everywhere on its domain. But we can say more. Not only are they continuous functions, they're also nice and smooth. They've got no corners. And that's because they're differentiable everywhere on their domains. But are all functions which arise in practice as well behaved as these? David?
Well, Robin, not if we combine them. For example, if we multiply sine x and 1 over x, we get this function sine x over x. And that's continuous everywhere in its domain. And that's everywhere except 0, where we seem to be dividing by 0. But we've seen that if we define y to be 1 when x is 0, the function here is continuous as well. And that's because sine x over x tends to 1 as x tends to 0. And sine 1 over x is similar. It's another function that's defined everywhere except 0. And that's because of this term 1 over x. And it's continuous on its domain too. But there's a difference. There's no way it can be made continuous at 0. Because for these values of x, y is equal to 1. And for these values of x, y is equal to minus 1. So there's no limiting value as x tends to 0. Well, what about this function, x sine 1 over x? Again, it's continuous everywhere on its domain, which is the whole of R except 0. But this time, it looks as if we can define f at 0 to make it continuous here too. Because sine takes values only between plus and minus 1, this product takes values between plus and minus x. So the values of y on this graph are squeezed between the two lines y equals plus x and y equals minus x. So if we define the function to be 0 when x is 0, this function is continuous on the whole of R. Now, this function mod x is different. It's defined and continuous on the whole of R, including 0. But it's got a corner here at 0, so it's not differentiable at 0. Although it is differentiable everywhere else. In fact, all these functions are differentiable at points other than 0. But what about 0? Well, this function has the same behavior at 0 as mod x. Y equals mod x meets the graph as close to 0 as we please. So this function can't be differentiable at 0 either. Now, this one's easy. No matter how we define this function at 0, it's not continuous there. And so it can't be differentiable at 0 either. Remember that every differentiable function must be continuous. But it's not true the other way around. Now, we defined this function to be 1 at 0. So it's continuous at 0. And it looks as if it's differentiable at 0 too. Unlike the other three, it is. Actually, its derivative here is 0. Now, many of the functions we meet in analysis are both continuous and differentiable. But not all functions are like that.
All the functions we've seen so far are defined by a simple formula. Y equals something involving x. But a function doesn't have to be defined by a formula at all. The thing is that for each value of x in the domain, there's just one image point in the codomain. But historically, even that simple idea took a long time to evolve. In the early 18th century, the Swiss mathematician Johann Bernoulli wrote this definition.
A function is a quantity composed in any manner whatever of some variable and of constants.
In other words, he thought of a function as a formula. But later it became clear that this rather woolly description just isn't good enough, since there are many functions which are not given by formulas. A more precise definition was given in the mid-19th century by Riemann.
Let us suppose that x is a variable which can assume all possible real values. If to each of its values there corresponds a unique value of the indeterminate quantity y, then y is called a function of x. It makes no difference whether one defines the dependence of y on x as an arbitrary one or as one determined by certain operations.
This is much closer to the modern definition, which is very general. The main idea is that for a function, each x value in the domain gives rise to exactly one y value in the codomain. But the function doesn't have to be defined by a formula. But with such a general definition, what sort of functions do we get? How strange can they be? All our functions so far have been continuous everywhere, except possibly at just one point. But can we get more discontinuities? In fact, can we get infinitely many discontinuities? Let's start with the zero function, which maps every real number to 0. If we want to get a function with just one discontinuity, we can map all non-zero values of x to 0, but map the point 0 to 1. We get more discontinuities by mapping all the integers to 1, giving a function continuous everywhere except at the integers. So that's a function with infinitely many discontinuities. But we can be even more perverse. We can map all the halves to 1, and the thirds, and the quarters, and the fifths, and so on. In fact, we could map all the rationals to 1, but we'd still have infinitely many irrationals mapped to 0. So this function, called Dirichlet's function, is defined by f of x equals 1 if x is rational, and 0 if x is irrational. And the graph looks rather like these two parallel lines. But really, each line has infinitely many gaps in it. In fact, this function is discontinuous at all points. Even stranger is a function defined by Riemann. This time, instead of mapping each rational number to 1, we map each rational p over q in its lowest terms to 1 over q. What does the graph of this function look like? Well, as before, the irrationals all get mapped to 0. How about the rationals? The integers all have denominator 1, so they map to 1. All the halves map to 1/2. All the thirds map to 1/3. And the quarters, and the fifths, and the sixths, and so on. Now you might think that this function is discontinuous everywhere. It's certainly discontinuous at all the rationals, but surprisingly it's continuous at all the irrationals.
Now, both of those functions had infinitely many discontinuities. But suppose we have a function that is continuous. Can it have infinitely many corners? Well, let's take as our starting point the function mod x. Here's the mod x graph. If we bend the lines at plus and minus 1/2, plus and minus 1, and so on, we get more corners. It's a sawtooth graph, and it's got infinitely many corners. So, if we call it the graph of the function f, then f has infinitely many points where it isn't differentiable. Now we can repeat this bending idea to get a graph with even more corners. Let's look just at the interval between x equals 0 and x equals 1. This function has twice as many corners as f had in the interval 0, 1. And the rule for this function is that y equals a half f of 2x. If we repeat this bending process again and again, we get a sequence of functions whose graphs have more and more corners. Each new graph is just the preceding one, scaled by a factor of a half in both the x and the y directions. Here are the first three of those functions again. F of x, a half f of 2x, and a quarter f of 4x. They're all continuous. But all their graphs have corners. So at these points, that's at a half on this graph, at the quarters on this one, and at the eighths on this one, the functions aren't differentiable. So, what about the sequence of such functions? Does this sequence have a limit? And if it does, what is the limiting function? Is it continuous? And if it is it differentiable? Well, the sequence does have a limit. But because the height of each graph is just a half the height of the preceding one, the limiting function is the 0 function. And that graph is the line segment 0, 1. Now that's certainly both continuous and differentiable everywhere. But it's not very interesting. It's lost all these corners. So can we get a function that's continuous everywhere, like these, but differentiable nowhere? Well, we can, with a bit of care. Now, another way of producing new functions from old is to add up the ones you've already got to get a series. We got functions like sine x and e to the x by adding up powers of x. So, what happens if we add up all the functions in this sequence? Does this series converge? And if it does, its sum is a function of x. What properties does that function have? Is it continuous or differentiable? Well, let's look at the sequence of partial sums for this series. Here's f of x. And here's the second term, a half f of 2x. Adding them together gives this function. Here's the third term in the series, and the third partial sum. We do seem to have preserved some of the corners, but not all of them. So let's add in the fourth term in the series. Here's the fourth partial sum function, and its graph looks a bit more promising. If we continue adding in terms, the graphs of the successive partial sum functions are all continuous, but they have more and more corners. And so more and more points where the partial sum functions are not differentiable. The limiting function has this interesting graph. It's continuous, all right, but is far from smooth. In fact, we'll show that it's nowhere differentiable. And here's our limiting function, b of x. It looks rather like a blancmange. So, the sum of our series, this function b of x, is continuous everywhere. But is it really differentiable nowhere? Well, let me try to convince you of this. Suppose we're interested in this point. Well, we use chords whose endpoints are on either side of it. And if b is differentiable here, then as the two endpoints approach our point from either side, the slope of the chord will tend to the value of the derivative of b there. So, let's see whether b is differentiable at a third, for example. Let's take this as our first chord. Its endpoints have x equals 0 and a half. The slope of this chord is 1. For the second chord, let's take x equals a quarter and a half, and the slope of the second chord is 0. Our third chord has endpoints where x equals a quarter and 3/8. That's got slope 1. And if we keep bisecting in this way, then a third lies alternately in the left and right halves. And the slopes of the chords alternate between 1 and 0. So the sequence of slopes doesn't tend to a limit, and b can't be differentiable at a third. So our Blancmanges function is continuous everywhere, but nowhere differentiable. The first function with these properties was discovered by Weierstrass in the middle of the 19th century, and it caused a sensation at the time. Now, what's the point of all this? Do functions like this have any practical value, or were they invented by mathematicians for purely academic interest? Indeed, many mathematicians before the 20th century regarded such functions as monstrous and pathological. In 1893, the mathematician Hermite talked about
turning away in fear and horror from this lamentable plague of functions with no tangents.
So is that a reasonable point of view? Do functions with no tangents have any use? Well, such curves do arise in nature, where things often do happen in a very irregular way. In fact, if we slightly change the way that we construct this Blancmanges function, we can get a graph which looks more like shapes we see in the natural world. As before, we start with a triangle with base 0, 1. But this time, we choose the third vertex at random. This splits 0, 1 into two parts. On each of these, we place a triangle, again chosen at random, and add it to the previous one. Continuing in this way, by adding in more and more triangles, we get a limiting sum function that looks like a mountain range. This picture was produced by a mathematician called Mandelbrot using the same kind of methods, and it looks remarkably like the real thing. And in fact, the ruggedness of a mountain profile can be measured using these ideas. They can also be used in another geographical problem. How long is the coastline of Britain? The closer you look at it, the longer it seems to get, and the more wiggly it appears. It looks as though the coast of Britain has infinite length.
In fact, mathematicians introduced closed curves of infinite length long before scientists began to ask questions about the length of coastlines. Here's one which is called the snowflake. It was devised by von Koch in 1904. It's built up as the limit of simpler closed curves. Here's the first curve. It's an equilateral triangle. To get the next curve, each side is divided equally into 3, and a triangle drawn on the middle third of each side. This process is then repeated over and over again, producing irregular curves which get more and more convoluted. In the limit, we get a shape like this. It's called a snowflake curve, and it has the remarkable property that the length between any 2 points on the curve is infinite. Now you may feel we've got a long way from functions. This curve can't actually be described by a single function from R to R. But remember that we can describe curves in the plane parametrically. For example, here's the cardioid again, and it's described using 2 coordinate functions of another variable, t. One function for the x-coordinate and one for the y-coordinate. And we can use that idea with this snowflake as well. The first stage was an equilateral triangle, and that's generated by these 2 coordinate functions. The x1 is at the top. The corners on these 2 graphs for x and y correspond to the corners on the triangle. Later approximations to the snowflake have more and more corners, and so do the corresponding coordinate functions. Actually, in the limit, each of these functions is both continuous and nowhere differentiable, just like the Blancmanges function. We can use this method, that is, taking a basic shape like a triangle and distorting each side over and over again to produce a whole variety of different closed curves. And if you do this randomly, here's the sort of curve you get. This one looks much more like a coastline. And here's another one. We start with this shape, and the rule is to replace each side by this. Here's the first stage. And if you apply this process several times, this is what you get. It looks much more like a snowflake.
And here's a model of that snowflake. This time I think you'll agree that it looks very much like the real thing. So starting with some very simple functions, we've been able to build up some very strange ones, such as the Blancmanges function. We've also seen some very strange curves in the plane, some of which have infinite length, and also seen to model natural phenomena. To end with, let's look at a variation on these ideas. We'll take a line segment as our basic shape, then add a spike, giving us 4 line segments, along, up, down, and along. We now add a new spike to each of these line segments. And then we do it again. And so on. This time, the limiting curve looks rather like a forest. Let's see what happens if we make the spike just a little bit longer. The limiting curve is again a curve of infinite length. But this time, it passes through every point of a triangle. It's called a space-filling curve.